All right, so tomorrow we're going to be in lab fitting a dynamic Beverton Halt model to data from a harvested population of abalone from Baja. We are going to run into a couple violations of model assumptions, and we haven't really dealt with model assumptions so far in the last few models we've done. So I want to take this lecture to introduce the assumptions for a model that assumes a normal distribution and hint at how we might address some of those assumption violations. So let's start with just this really simple linear model that we're familiar with by now. So we have mean mu, or y hat, is a linear function of x, and y is normally distributed around mu with some variance sigma squared. What this implies is that at any given value of x, y is expected to be normally distributed, and it has a constant variance. So we can visualize the distribution of y, the assumed distribution of y, as sort of this normal distribution that's moving along this axis with only the mean changing, not the variance. And this is important because the variance is not linked in any way to x. So let's define epsilon as the error, and it is what we get when we subtract the random variable y from the expected value of y, which is mu or y hat. And epsilon is a random variable, right? Because it's a function of a random variable, y. And then let's reformulate this model so that we can kind of make inferences about the distribution of epsilon. These are the same model. So we have y is a linear function of x plus some error epsilon, with epsilon normally distributed with a mean of 0 and a variance of sigma squared. And these are the exact same model. I've changed nothing at all here. I've just kind of moved around some values. So this implies, obviously, first off, this assumption we'll call the linearity, and it's obvious because it's stated right here. The expectation of epsilon for any value of y, and it says x here, but I use x to indicate just a random variable. So for any value of y or of x is expected to be 0, right? And then we have the homoskedasticity assumption, which is that the variance is constant for all values of y or x, and that's again implied because sigma squared is not linked in any way to x or y. We have the independence assumption, the assumption that the errors are independent of each other means that if I told you the error, the expectation of the error at x equals 4 or something, you would not be able to tell me anything additional about the expectation of the error at x equals 5. Having information about the errors at one value of x or y doesn't tell you anything about the errors at other values of x or y. We always just expect them to be normally distributed identically and independently with mean 0 and variance sigma squared. And then we have the normality assumption, which is probably the most obvious one because it's written right here. We expect that the errors are normally distributed. So one important distinction between the term residuals, which I'm sure you've heard, and the term error, the error is a random variable. So because it is a function of uppercase y, it is an unrealized random variable. The residuals are a realization of that variable. They're what we get when we subtract lowercase y, which is our observed y values, from our fitted values y hat, right? And that's an important distinction. So let's just go over a couple quick examples of what models that do or do not meet these assumptions can look like. So let's say here that y is normally distributed with even variance across around this regression line as a function of x, right? This pretty clearly meets the assumptions. Y is normally distributed at any given value of x, and the variance is constant, so it's homoskedastic. Here we have a model which breaks the homoskedasticity assumption, because, well, it's heteroscedastic. The variance in this distribution is increasing as we increase x. And then we have a model which is non-normal. It's clearly skewed, but it's homoskedastic, such that the variance is similar across the range of x values. And then we have a model which is neither normal nor homoskedastic. And in both of these examples, the variance is increasing with the mean, but this will always be the case. It's probably the most common pattern, especially in count data, but there can be violations of the homoskedasticity assumption that don't result in the variance simply increasing with the mean. So we can evaluate the linearity and the homoskedasticity assumptions by plotting the residuals against the fitted values. So the residuals, again, are little y, the observed values of y, minus y hat are fitted model values of y, what we expect given the parameters of the model. And we plot those against y hat. And for a model that's really well behaving, what we expect is, if we were to take sort of a moving average here, the expectation, or the mean of the residuals rather, is more or less hovering around 0 this whole time, which tells us that the linearity assumption is definitely met here. And then if we look at the spread of the residuals around this axis, it's pretty even as we increase the value of y hat. And so that tells us that it's pretty safe to assume that the errors are homoskedastic as well. Now in this model, we still have met the linearity assumption. The mean of the residuals is pretty close to 0, no matter where we are as a function of y hat, but the data are heteroscedastic. The model is heteroscedastic. So we're seeing that the variance in the residuals is increasing as we increase the value of y hat, which results in this fanning pattern, which is pretty common. Here's an example where the data are homoskedastic, where the variance is similar across the range of fitted values of y, but the linearity assumption is violated. If we were to take a moving average here, we would see that that the residuals tend to be positive around intermediate values of y hat. And one way this can arise in a linear model is if we're fitting a line to something that's actually a curve, if there's a curved relationship between y and x. And often it isn't possible to actually achieve perfect linearity in nonlinear models because the model is constrained to a certain functional form. So unlike in a linear model where you expect the mean of the residuals will be about 0, in a nonlinear model that will frequently not be the case. But typically we'll prefer models that get closer to that because they're less biased. We can evaluate the normality assumption by just plotting histograms of the model residuals and seeing if they look approximately normal, or by plotting the quantiles of the residuals against the normal distribution's theoretical quantiles. So if we plot the quantiles of the residuals against the theoretical quantiles of the normal distribution, and they match up really well, falling on a one-to-one line, then that would tell us that the residuals are approximately normal. And here we have data simulated from a normal distribution, which match up really well with the quantiles of the normal distribution. If the residuals are definitely not normal, if they deviate from normality quite a bit, there will be obvious patterns in the quantile, the QQ plot. In this case, the data are really concentrated around the mean, and there are less observations in tails than we would expect. Here, the data are skewed, and again, we have a clear pattern arising in the QQ plot. What we can't do is evaluate the normality assumption by plotting the response variable itself. Normality is a model assumption. It's not an assumption about the data. So in this example here, I have simulated x from a uniform distribution, and I've simulated y as normally distributed around a linear function of x. So I know that these data meet the assumptions of a linear regression. However, if I plot the marginal distribution of y, which is just the overall distribution of y, what I see is that y is more or less uniformly distributed. So if I were going off of the distribution of y as an indicator for whether or not these data meet a regression, I would come to the wrong conclusion here. What matters is the distribution of y around the fitted values. So we always want to use the residuals when evaluating the normality assumption. There are many ways that the errors can depart from the independence assumption, one of which is temporal autocorrelation. We will cover this tomorrow in lab, but this is when data at adjacent time points are correlated, when residuals at adjacent time points are correlated. So if you know that the residuals at time t are positive, then if the data are temporally autocorrelated, you know that the residuals at time t-1 or t+1 are also likely to be positive, right? This can also occur from seasonality that isn't accounted for in the model. Then there is spatial autocorrelation, which is a pretty simple extension of this idea. This is when errors are correlated for data that are close together in space and less correlated for data that are further apart in space. And then we have clustering. This is when observations are grouped in some way that we're not accounting for in the model. So if I surveyed C stars on 5 transects in each of 10 sites, and I counted the number of C stars in each transect. If I didn't account for the fact that the observations, the C star counts, are grouped according to site with multiple observations per site, then these data are clustered, and you'll often hear this referred to as pseudo-replicated. Just before I go on, I want to point out that these assumptions I outlined are not the same for every distribution you choose, right? So one example here is, let's assume that y is instead Poisson distributed. We're no longer assuming that the variance stays the same in y as the fitted values of y increase, right? Because lambda, which here is a linear function of x, is both the mean and the variance of the Poisson. So we would expect for a Poisson model that as the fitted value of y increases, the variance in y also increases. And this is not a problem, it's what we expect. So the rest of this lecture, I'm just going to go over a quick example. I have simulated data here from Beverton-Holt density-dependent model for population growth, and then I fit a curve to it. And what you can see here is that this curve in black underestimates the observed population trajectory for a good 50 or so time steps, right? And so this is already clearly violating the linearity assumption because the model is downward biased for a good chunk of the time that we're observing this population for. We compute the residuals by taking the deviations of the observed values from our expected values. And if we plot these as a function of time, what we can see is a very clear autocorrelation here. If I know that a residual is positive, I also am likely to know that the adjacent residuals are also positive. And if I know that a residual is negative, that tells me that the adjacent residuals are also going to be negative, right? And if the data were independent, or if the residuals were independent, then what I expect was more or less even scatter over time, where knowing the residual at any one time point does not tell me anything about the adjacent time points residuals. So we can assess the extent of the residual temporal autocorrelation by plotting the autocorrelation function for the residuals. This is just the correlation between residuals at time t and t minus some lag. So here on the x-axis we have that lag, and on the y-axis we have the correlation coefficient. The correlation between observations at time t and t minus 0 is just the correlations between the residuals and themselves, which is of course 1. And then the correlation at a lag of 1 is the correlation of the residuals at time t and in the previous time step t minus 1. So we can see that it's quite high. The lag 1 autocorrelation is 0.9. And we can evaluate as well the partial autocorrelation function, which shows a correlation of 0.9 at the lag 1 autocorrelation. Notice the axis is shifted here, but shows no autocorrelation after that. And the reason is because the partial autocorrelation is adjusted for lower order lags. So the lag 2 autocorrelation is adjusted for the lag 1 autocorrelation. And the blue lines here, by the way, are the confidence interval for the correlation between 2 white noise time series. So things that fall outside of those lines are what we consider significant correlations. So there's clearly temporal autocorrelation here. Knowing the residual 1 time step tells me a lot about the residual in the next time step. And this is something that we'll find or look at one method of dealing with in tomorrow's lab. Now here I'm plotting the residuals as a function of the fitted values. So we have the observed value nt at time t minus the predicted value, and we're plotting as a function of the predicted of the fitted value, right? And what we can see is that as the population size, the fitted population size increases, there's a pretty clear trend here. We're clearly violating the linearity assumption. And not just that, but we also have heteroskedasticity. So the variance in residuals is quite low for low population sizes, and then it balloons as we increase the population size. We can plot a histogram of residuals to assess normality. Here it's a little bit hard to tell because histograms, when you change the bin size, you'll also change the shape of distribution. So a better thing to do is to plot the QQ plot. And we can see that there's no very clear departure from normality here. There's no obvious pattern in these residuals, but they're not exactly perfectly normal either. So the solution to these problems depends on which of the assumptions is violated. If we have departures, clear departures from linearity, then we can perhaps change the functional form of the model. Maybe here, I would try, if I didn't know that the model data was simulated from a Beveridge and Holt, maybe I would try other forms of density-dependent population models, for example, a generalized logistic model. We could also add in model components, or, and we'll find out what this means tomorrow, but modify the covariance structure of the errors to fix departures from independence. And tomorrow we'll be addressing temporal autocorrelation. Or we can transform the data or change the distribution response to correct homoskedasticity. For example, here we have data which are discrete because they're really counts of the number of individuals in each time step. And those data display an increase in variance at higher population sizes. And that is maybe a good candidate for a Poisson model. So we'll be exploring these tomorrow in class when we look at fitting a Beveridge and Holt model to a harvested population of abalone. And see you tomorrow.